Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems, ISC. Today's talk is by Dr. Shashank Vatedka, and he will be speaking on distributed compression with random access. Dr. Shashank received his MSc Engineering and PhD degrees from the Department of Electrical Communication Engineering, Indian Institute of Science, Bengaluru in 2017. During 2016 to 2018, he held research assistant and postdoctoral positions at the Institute of Network Coding, Chinese University of Hong Kong, Hong Kong SAR. During 2018 to 19, he was a postdoctoral fellow at Telecom Paris, France. Since October 2019, he is an assistant professor with the Department of Electrical Engineering, IIT Hyderabad. He was a recipient of the TCS Fellowship during his doctoral studies and the Sheshagari Kaikini Medal for Best PhD thesis in the Department of Electrical Communication Engineering, ISC Bengaluru. He also received the Best Paper Award Honorable Mention at SPCOM 2020 and the Best Poster Award at the 2021 Stanford Compression Workshop. His primary research interests are in information theory and coding, with application to data compression, security, and statistical inference. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Shashank directly or type them in the chat box and we'll moderate it with him. Over to you, Dr. Shashank.
Thanks a lot. Thanks to the organizers for kindly inviting me to give this talk. So today I'll be just talking about this problem of distributed compression with random access. This is some recent work that I've been doing with Aslan Chamketin, who is at Telecom Paris in France, and Venkat Chandar, who is at D. Shaw in New York. So throughout the talk, if you have any questions, please feel free to ask me in between. Please feel free to stop me. So I'll get on with the rest of the talk. All right. So when I use the word compression, what first comes to mind? So the first thing that comes to mind are utilities such as zip or rar or gzip. We've all used these in our day-to-day applications when suppose we want to send a folder over email or a large file over email, or we want to say download something from Google Drive. These are automatically zipped and downloaded, right? So these classical, what I call classical compression algorithms, such as zip or rar or gzip, these are based on what are called the Lempel-Ziv class of algorithms. These are optimal in several respects, as one would have seen in a course on information theory. But unfortunately, these have been mainly designed for the purposes of archival. What do I mean by that? Well, typically, you have a folder or a collection of files. You compress these, and then you either send it to someone or you store it somewhere. And when you want to recover it, you essentially decompress the entire file. You extract the file using the zip or the rar utility, and then you read the file, you edit the file, and so on. Right. So this is what I mean by in general by archival. But today's needs are different. We're not just interested in say storing files, but also largely in processing files. Today, most of our data is not stored on our computers or smartphones. A lot of it is actually stored on the cloud, right? And we're in our day-to-day applications, we are always interacting with this data on the cloud. So there are several applications. So for example, even if we take the example of Google Drive, So we're typically Google offers around say 10 to 20 gigabytes of free space, and we store a lot of data on Google Cloud. Now, after all, storage space is expensive, and all of this data is being stored on some server on the cloud, in some data center. Now, we're constantly accessing these files on the cloud. So, for example, if you want to edit a Word document, or if you are interested in reading or editing a spreadsheet, we're in fact directly interacting with that file, which is stored in Google servers. So all of this data are which is hosted on either Google Drive or Dropbox. We're constantly interacting with it by downloading maybe some of the files to our local machines. We're modifying it and we're updating it. Now, Google, after all, wants to save space, because after all, more space implies more money. But every time you extract a file, or when you compress a file, this takes computational power. All right. So Google wants to save space, so it may want to compress all your files and folders. But every time you want to access, modify, and update it, these files have to be extracted, edited, and then recompressed and stored. And this is expensive. If you use a traditional compressor such as zip or gzip, there is no way of editing the file directly in the compressed domain. You have to extract the file, edit it, and then again recompress the file. So there are many applications such as cloud storage, or even genomic collections. So a single DNA sequence for one human being can be huge. So they consist of around 1.8 billion base pairs, which is and collections of genomes of several individuals. These data sets can be several gigabytes or terabytes in size. And you want to save space, so you should of course compress it. But if you use a compressor such as zip, then every time you want to say access some small part of say one genomic sequence, maybe you want just to extract one genome of the third individual, you have to essentially decompress the entire collection and then read it and then recompress the entire collection, which is wasteful, and that is exactly what we want to avoid. And why is this important today? It's, well, a lot of our data is stored on the cloud, and one estimate says that around 70% of the global internet traffic is because of communication between data centers or between users and data centers. So all the more we need schemes, or we need efficient mechanisms to store this data on the cloud, and at the same time also be able to manipulate it as efficiently as possible. So compression is good because it saves space, but editing compressed files is hard, and manipulating compressed files is hard. So what we are asking for is sort of the best of both worlds. We want storage as good as you would get using zip or gzip, but also efficient manipulation as though you were operating on the uncompressed file itself. So can we achieve both, or is it too much to ask for? So in this talk, I'll speak about one specific problem of compression with efficient manipulation. So I'll essentially focus on this problem. How do you efficiently store data, or how do you compress data such that short fragments of the raw file can be extracted as efficiently as possible? Let me put that more specifically. So suppose that we have a large file. Assume that you have a huge text file. In order to save space, you compress it using whatever utility you want, and this is stored somewhere, maybe on the cloud. Now all that you have access to is this compressed file. Now let us say that you don't want to recover the entire file, but maybe the second word of the raw file. Now, one thing you can do is, of course, you decompress the entire file, read the entire compressed sequence, and then decompress everything and then read the second word. But is there a way of doing it more efficiently? Now, suppose I can design an algorithm. I will call this algorithm the local decoder. So this local decoder does not read the entire compressed sequence. It does not read the entire compressed file. What the local decoder does is the following. It takes as input a particular location. Maybe you want to extract the second word. So you tell the local decoder that you want the second word of the raw file. The local decoder just reads a small number of compressed bits and then outputs the second word. Right? So this is what I mean by random access. I should be able to recover any symbol from any location in an efficient manner. And by efficient, I mean that I should be able to do it without reading the entire compressed sequence. Or I want to do it by reading the minimum number of compressed bits. All right. So this is for, of course, a single source, but I want to be more ambitious. What I want to solve is the following problem. Suppose I have two files which are correlated. Let me call them file 1 and file 2. I compress each of these files separately to get these compressed versions. Let me call them C1 and C2. Now I want to ask the same question. Now C1 and C2 should take minimum space. So the size of C1 and the size of C2 should be as small as possible. But at the same time, if I want random access, so if I want, let's say, the second word of the first file, I should be able to extract just the second word of the first file by reading a very small number of bits of C1 and C2. So in this particular cartoon example, I'm reading only 6 bits, so 4 bits from C1 and 2 bits from C2, and this outputs the word that I'm interested in. Now, what is important to note is that when you encode or when you compress these two files, you don't know which location is required at the output. So at the receiver, you have an input, which is the location that you want, and corresponding to that location, maybe the second word or the third word. So every time I give a particular location to the local decoder reads some of the bits of the compressed sequence, depending on which location has been specified, and outputs the word in that particular location. All right. Is there a question?
Yes. So when you mentioned
sorry, go ahead.
Oh, sorry. Please go ahead.
No, go ahead, please. I'll ask after you.
Okay. So when you mention location, or you are saying second word, that means you are assuming some kind of index, which is outside the compressed data. Is that assumption?
No. So the location here refers to the location in the raw file. So this is what I call the raw file. These are the actual, maybe these are text files, whereas these are the compressed versions of those text files. Okay, if you take that as an example. And whatever location is specified, it's assumed that this is a valid location. That is so for example, if the first file has 100 words, then the location specified is something less than 100. I'll make this more formal as we go along, but but definitely please.
Okay, so in this case, when you say a location, is it a fixed location like nth byte, or is it subject to some? Okay, not subject to some conditions or delimiters.
No, so that's not particularly important as to whether it's the first word or the first character or the first byte. We'll abstract all of that out, but whatever it is, it's known to everyone. So what is meant by the meaning of the location or in a particular file is well specified.
Okay, thank you.
Yeah, thanks.
Okay, so I also just wanted to understand the same thing, that the location is referring to the location in the uncompressed or original file.
Exactly.
Okay. All right. Thank you.
Any other questions? All right. So what we want is to design a compression algorithm which minimizes the storage space, but at the same time also minimizes the number of compressed bits which are required in order to recover a single message symbol, right? So before I talk about this sort of a scenario where I have multiple files, let's talk about the single file problem or the single source problem. All right. So how do you compress a single source such that you can also achieve random access on the compressed files? Now, in this talk, I'll assume that people have some familiarity with information theory. Even a basic course in information theory is sufficient, but it's not essential. I will try to keep things. I'll try to sort of say things from scratch, but certainly some familiarity with even a first course in information theory would be very helpful. Okay, so let's look at the basic fixed length compression problem. All right, so this is just what you would see in Information Theory 101. So what is the problem? You have a raw file or the uncompressed file, which I call xn. So it consists of n symbols, which could be n bytes or n words or n characters. So we'll assume that each symbol, so this is basically an n. So for us, mathematically speaking, this xn is an n-length vector where each symbol xi comes from some finite alphabet which is known. To keep things simple, I'll assume that this source is memoryless. So this is a random sequence where each component is independent and identically distributed according to some known distribution px. So I'll assume that this is known. Right. A lot of these assumptions can be relaxed, but I want to keep things as simple as possible. So the basic compression problem is the following. I'm not talking about random access for the time being. So the goal is to design these functions, the encoder and the decoder, or sometimes also called the compressor and the decompressor, which do the following. So the encoder takes as input the source sequence xn and outputs a sequence of bits, the compressed file or the compressed sequence. So this is the compressed sequence, which is of length nr. It consists of nr bits. And the decoder takes as input the compressed sequence and outputs an estimate of the actual raw sequence xn. I will also sometimes refer to this as the source. So xn is the source and xn hat is the estimate. And the goal is to, of course, make sure that nr is as small as possible. So the compressed file should be as short as possible. But at the same time, I also allow a certain probability of error. So xn is a random sequence, and I permit xn hat to be xn with a very tiny probability. And Shannon's source coding theorem says that this is indeed possible as long as r is a certain amount. So more formally, so for every small tiny epsilon greater than 0, it is possible to construct this encoder and decoder, or the compressor and a decompressor, whose rate, or this r over here is what I call the rate, is equal to the entropy of the source plus epsilon, and for which the probability of error of decoding the original source sequence decays exponentially in n. So here, h of x, if you are familiar with it, so this is just summation over all symbols x, p of x log one over p of x. All right, so the entropy is sort of the fundamental limit of compression. As long as you demand a compression rate of h of something greater than the entropy, you can achieve a vanishingly small probability of error. So it's good if you've seen this before. If not, just it's important to note is that it is possible to design these encoders and decoders operating at rates close to the entropy, for which the probability of error decays exponentially in. So this exponentially decaying in n is something that will be important in a little bit. So let's focus on some toy examples. Let's look at a Bernoulli source and see how one would try to prove this achievability part of the source coding theorem. This is basic, but let's still try to do it from scratch. So the main idea is that you don't want to. So for a Bernoulli sequence, I assume that xn is a binary sequence. It's a random binary sequence where each component is IID Bernoulli P. So each component is either 0 or 1 with the probability that xi equal to 1 equal to p. All right. So instead of encoding all the sequences in this in the set of all, in the space of all binary sequences, you only focus on those which are most likely to occur. So we define a typical set, which is the set of all sequences for which the number of ones is roughly close to np, right? So if you have an IID Bernoulli P sequence, then we know that with very high probability, the number of ones in the sequence is close to np. So you define the typical set as the set of all sequences for which the number of ones is close to np. Now, just using combinatorial arguments, essentially just Stirling's approximation, you can show that the size of this typical set is roughly equal to 2 raised to n times the entropy. And the probability that a random sequence does not lie in the typical set decays exponentially in it. This is just by, say, Chernoff bound. All right. So we know that the set of all typical sequences or sequences which are likely to occur are, I should say the set of all typical sequences. This is just a set of size 2 raised to n times h of p. So if you look at the space of all binary sequences, the typical set is a strict subset. All right. And since you know that with very high probability, a random sequence is guaranteed to lie in the typical set, it's enough only to assign distinct code words to those in the typical set. So what you do is that for each sequence in the typical set, you assign a unique binary sequence, and the number of and the length of the binary sequence required, the shortest length of the binary sequence required to uniquely label each point in the typical set is just n times h of p. Right? So you can achieve r close to n times h of p, and the probability of error decays exponentially in it. Right? Sorry if it's a little bit repetitive, but just want to make sure that this is okay. All right. So this is the sort of the basic problem of compression, standard stuff. Now what we want is something more. All right. So the first part of the problem still remains the same. We have a source sequence xn. Once again, let us assume that this is Bernoulli P, IID components with Bernoulli P, and this is compressed to give a compressed sequence. It's a binary sequence of length nr. Now, what is different about this is the decoding. So what we want to construct is not just a standard decoder, but what I call a local decoder. The local decoder takes a location I. So I is between 1 and n. So it takes a location I as input and is expected to output an estimate of the ith symbol, xi hat. But what is the local decoder allowed to do? It's allowed to read a small number of bits of the compressed sequence. So maybe I say I equal to 2. So the local decoder gets as input I equal to 2. And after seeing that it wants the second symbol, let us say that it probes the second bit of the compressed sequence, the fourth bit of the compressed sequence, and the nth bit of the compressed sequence. So it reads 3 bits of the compressed sequence, reads what these values are, and then outputs xi hat. So that's an example of what a local decoder is supposed to do. All right. Any questions here? Okay. So one assumption that we will make is that this local decoder is non-adaptive. So when you design the encoder and the local decoder, you specify for each I the set of locations you're supposed to probe. So for example, if I equal to 1, for I equal to 1, you're supposed to probe maybe locations 1, 3, and 4. For if I equal to 2, then this is supposed to probe the local decoder reads the second, the 7th, and maybe the 4th bit, and so on. Now this is of course part of the design problem, how you select I1, I2, and so on. But these are decided beforehand, even before you know which particular symbol you want. Okay, so in particular, so this is what I mean by non-adaptive. One can also study the problem with adaptive local decoders, where this set is not decided beforehand, but in fact you can decide, you read a certain number of bits, where the next bit to read, which location you read, could potentially depend on the value of the bits that you read up to now. All right. So for now, just to keep things simple, I want to eliminate such local decoders. I'll assume that these have been designed beforehand. All right. And the goal, of course, is to minimize the rate, and at the same time also ensure that the number of bits you need to probe in order to recover any particular xi is as small as possible. So the local decodability of a particular algorithm is going to be the maximum number of bits, the maximum number of compressed bits that you need to read in order to recover any particular xi. All right. Any questions here? Okay, so it's a fairly simple problem to state, but it turns out that it's only very recently that this problem was solved. So before I proceed, I'd like to remark that similar problems have been studied both in the computer science and the information theory literature. In the computer science literature, it's been studied for a very long time now, and it generally falls under the broad framework of what are called compressed data structures. The model there is slightly different. Typically, the input or the source sequence is not assumed to be random. You want to design an algorithm for the worst case input, and the way you define local decodability can vary. So one particular model, where there's a lot of work, is the so-called word RAM model. So here, the efficiency of a local decoder is not measured using the number of bits that the local decoder probes, but rather the time required in order to in order to recover a particular symbol. So the general assumption here is that any operation on a sequence of order log n bits, so any operation on a chunk of size order log n takes unit time, and so any read or write or any sort of arithmetic or logical operation on a chunk of size order log n takes unit time, and you want to measure the time required for local decodability. So that is typically what is called the word RAM model. And in the word RAM model, it is known that you can compress any sequence to the empirical entropy and still be able to locally decode in just constant time. So that's a surprising result, but that is but that can be done in the word RAM model. What I have been talking about is the so-called bit probe model, where the efficiency of a local decoder is measured in terms of the exact number of bits of the compressed sequence you need to read in order to recover, decode a particular symbol xi. Now, in the word RAM model, you need to read at least order log n bits because that is how the algorithms are specified. But in the bit probe model, potentially you could do away with order log n. Potentially you could recover a particular xi by probing fewer than order log n bits, maybe just a constant number of bits. And whether that can be done is what we want to answer. So in the information theory literature, this class of problems falls under what are called locally decodable source coding problems, and they've been studied since around 2013 or so. So here the assumption is that the source sequence to be compressed is a random sequence, and the efficiency is measured using the number of bits, the compressed bits that you need to read in order to recover a particular symbol. Okay. So with this, so just to summarize what we want to design a compression scheme whose rate is close to the entropy. So essentially you're getting the same compression performance as zip, but also you want to be able to recover a particular xi by probing at most a small number of bits. So this is what I call the local decodability. So this is a parameter called the local decodability. So we're looking at fixed length compression algorithms. So we also want to ensure that the probability that this estimate is off is as small as possible. So the question is, how small can, so assuming that we want a rate close to the entropy, what is the trade-off between the local decodability and the probability of error? That's exactly what we want to address in this, in at least the first part of this talk. All right, any questions? All right. So if you look at this problem, what's the first sort of solution you would come up with? The simplest thing that you could think of is you do the following. You have a large sequence and you want to be able to recover short fragments or individual symbols efficiently. So instead of compressing the entire sequence in one go, you instead split your sequence of length n into smaller subsequences and compress each subsequence. Right? So you have xn. Suppose that you break it down into chunks of maybe b symbols each, where b is much smaller than n, and you compress each chunk of b symbols separately, independently, using a standard fixed length compressor. Right? So that's a simple solution, and in fact that is what is, or some version of this is what is implemented in the industry today.
Shashank, one quick question.
Yes.
In the previous slide, is it true that you can also assume the same trade-off? I mean, you can look at it as if I fix the probability of error and the trade-off between rate and local decodability. Both are equivalent, I guess, right?
Yes, but we'll see why this is perhaps a little more interesting. So we're okay as long as it is approximately close to the entropy. Mm-hmm. But maybe by the time I get a little later, we'll see exactly what this trade-off should be and why it doesn't really matter.
Okay. Yeah. Sure. Thanks.
Just hold on to that thought. Sure. Any other questions? Okay. So the baseline solution is you split the sequence of length n into length b subsequences and compress each subsequence. So if you want to recover a particular symbol, maybe a symbol in this particular location, then you just need to decompress that particular subsequence and you're done. Right? So you can compress each subsequence into whatever, roughly b times h of x bits. So the overall compressed length is going to be n by b times h of x, which is roughly n times h of x. So you're still getting close to the entropy. And what is the local decodability? Well, you need to read this particular compressed subsequence. So this would be the size of this compressed subsequence. So this is just b times h of x. So you need to read b times h of x number of compressed bits to recover any individual symbol. All right. And what is the probability of local decoding error? Well, whenever a particular chunk is atypical, you cannot recover the individual subsequence. And therefore, the probability that the local decoder makes an error is equal to the probability that you cannot recover the original subsequence from the compressed sequence. So this is just the probability that subsequence does not belong to the typical set, and that is that decays exponentially in the length of the subsequence. So that's 2 to the minus some constant times b. And since the local decodability is some constant times b, the probability of local decoding error decays exponentially in the local decodability. All right. So for this particular baseline solution, if you want a rate close to the entropy, in fact, any rate for that matter, the trade-off between the probability between the local decoding error probability and the local decodability is exactly this. So that it's an exponential relationship. Right? Is this clear?
One question: does B have to be constant in this formulation?
Not necessarily. So it can be any B. For any given B, there's an exact relationship for this particular scheme. Right? So in particular, what you should perhaps observe is that if you want to recover the entire sequence xn with vanishingly small probability of error, then okay, so this is the probability of error of recovering a particular subsequence. The probability of error of recovering the entire sequence xn just by the union bound is just n by b times the probability of local decoding error. So if you want this to be vanishing in n, then b had better grow sufficiently fast. In fact, b should grow at least logarithmically in n.
Thank you.
Right. So if you demand that the local decodability be a constant independent of n, then the probability of local decoding error will also be a constant independent of n. Okay. So the question is, can we do better than this? Right. So is it possible to have a local decoding error probability which scales which is much smaller than 2 to the minus constant times local decodability? In fact, it turns out that this is possible, and that's a surprising result. And the main tool that was used to prove this is the following result by Berman and others. So this came from the compressed data structures community, and the tool is the following. So suppose that you have a sparse sequence. You have a binary sequence in which the number of ones in the sequence is at most epsilon times n, where epsilon is really tiny. So for every epsilon, it's possible to construct a locally decodable compression algorithm for which the compressed length scales. So the compressed length is small. It scales as order n times epsilon log 1 over epsilon. So it's not close to the entropy, but maybe some constant times the entropy. And any individual symbol of the sparse sequence can be recovered by probing only order log 1 over epsilon times the number of compressed bits. Okay. So it's a compressor specialized for sparse sequences, which does the following. It gets you some constant times entropy, compressed length, and the local decodability for sparse sequences is something which is small. So it's a constant, but it is independent of n. So that is what is important. Right. So this is independent of n. Right? It's a very powerful result, and it's basically a construction which uses expander graphs. Okay, so now let's try to use this particular scheme in order to improve over the baseline solution. So you take the entire sequence. Now you take B, that is the size of each subsequence or each block, to be a constant independent of n, and you compress each block independently using a fixed length compressor. So what can happen? So some of these subsequences, so some of them are going to be typical, some of them are going to be atypical, right? So maybe this one is atypical and this one is atypical. So this basically means that from the compressed sequence, you will not be able to recover this particular subsequence. From this, you will not be able to recover this particular subsequence. Now, since all of these chunks are independent of each other, on average, you would expect to see some constant times. So some constant times n blocks will be atypical. All right, and it's not possible to recover. And the probability of each block being atypical is decays exponentially in B, but B is just a constant, right? So but since suppose that this and this are atypical, then it is possible to recover the entire sequence from, of course, the compressed chunks, but also an error vector. So this is all those chunks. So it's a sparse vector which consists of all zeros, but only the chunks which are atypical are going to be stored here. So if the first chunk is atypical, then the error vector contains this particular sequence. If this chunk is typical, then this is the all zero sequence. This chunk is typical, then this is the all zero sequence. If this chunk is typical, then this is the all zero sequence. All right. So these consist of the atypical chunks. And the reconstruction, and from the compressed blocks, you can recover the typical chunks. So this can be recovered, this can be recovered, and this can be recovered, but this could not be recovered. All right. So it's possible to recover everything using just the reconstruction, using the compressed chunks, as well as this particular error vector. But this error vector is guaranteed to be sparse. So let us further compress this error vector using the sparse bit vector compressor of Berman and others. All right. Right, so you compress this error vector using the locally decodable data structure for sparse sequences. So this guarantees that the local decodability is just a constant, but the amount of space this takes is very small. It scales just as order n times epsilon log 1 over epsilon. If epsilon is sufficiently small, then the total space, the extra space taken by this locally decodable data structure is also small. All right, so what is stored are the compressed chunks of each of these blocks and the locally decodable data structure for sparse sequences. So from all of this put together, you can recover any individual symbol with vanishingly small probability of error. Right, so this essentially guarantees that the overall rate is the entropy plus some small constant delta. The overall local decodability is a constant independent of n, but the probability of local decoding error decays exponentially in n. Right? I'm skipping over some of the details, but essentially using this particular scheme, this is what you can achieve. Okay. Any questions?
Hi, Shashank. So here, maybe is it possible for you to very quickly tell how this probability of error is decaying with you?
Okay. So let's see. So the locally decodable, so there are two parts, right? One is the compressed chunks and this locally decodable data structure, right? So the local decodable data structure is guaranteed to output the correct bit as long as the sparsity is less than some epsilon times n. Correct? So as long as if sparsity, so in other words, if the number of atypical chunks, if this is less than some epsilon times n, maybe some epsilon prime times n, this is guaranteed to give the correct output. Right? It's you can recover the actual symbol exactly. So an error occurs in this entire scheme. An error occurs only if the number of atypical chunks is greater than some epsilon prime times n. But what is the probability that the number of atypical chunks is more than epsilon prime times n? Just again using a Chernoff type argument, that can happen only with probability 2 to the minus some constant times n.
Okay, so here you're assuming that B grows with n.
No, right? B is a constant. Right? So each chunk is of constant size, but the number of chunks is n by b, which is some constant times n.
Okay, sure. I get it now. Yeah. Thanks.
Any other questions? Okay. So just to summarize, suppose we want to compress a single source at rate close to entropy, then the baseline scheme achieves what I call weak locality. So the probability of the probability of error of the local decoder decays only exponentially in the local decodability. So if I want constant local decodability, then the probability of error is also a constant independent of n. But this two-stage scheme is much better than that. It is possible to achieve what I call strong locality, wherein the probability of local decoding error decays exponentially in n, even with the local decoding error, with the local decodability being a constant. So it's possible to achieve constant local decodability and exponentially decaying probability of error. All right. So all of this was for a single source, right? So the question is, does the same thing, does the same ideas carry on for multiple sources? So in particular, what I want to focus on is the so-called distributed compression problem, or sometimes called the Slepian-Wolf problem. So I have two sequences, two files, xn and yn. So the assumption is that these are correlated. So I have x1 up to xn. Both of them are of equal length, y1 up to yn. Each xi and yi are jointly distributed, they're correlated, and they follow some joint distribution pxy, but the components of xn and yn are IID. All right, so x1, y1 is independent of x2, y2 is independent of x3, y3, and so on. But each xi, yi is identically distributed with some known distribution pxy. Okay, and the goal is the following. You want to separately or independently compress xn into a compressed sequence CNR1, yn separately into CNR2, but then you can jointly decode. So the decoder has access to both CNR1 and CNR2 in order to recover xn and yn. So I've not introduced random access into this problem yet, but this is the basic Slepian-Wolf problem or the distributed compression problem. Okay, so of course here the goal is to ensure that R1 and R2 are as small as possible, and you should be able to recover xn and yn with a vanishingly small probability of error. All right, any questions regarding this particular problem? All right. So a classical result by Slepian-Wolf says that as long as R1 and R2 satisfy these constraints, so R1 is greater than h of x given y, R2 is greater than h of y given x, and R1 plus R2 is greater than h of xy, it's possible to separately encode x1 and xn and yn and use a joint decoder which operates at these particular rates R1, R2, and the probability of error can be made to decay exponentially in it, right? So it should be noted that this is better than it is better than using a standard point-to-point compression algorithm for xn and yn. If I encoded xn and yn using, say, a single source encoder, then I would only be able to get h of x and h of y. Whereas what is surprising is that if you have a joint decoder, then you can compress at rates below h of x or below h of y. You can bring it down to h of x given y or h of y given x, as long as this particular constraint is also satisfied. Okay, so let's use this as a given. If you've seen this before, it's good. If not, it doesn't particularly matter. But essentially, the ideas are similar to what we had for the single source problem. Okay, so we can ask the same question, right? So I separately encode xn and yn into two compressed sequences of different lengths, nr1 and nr2. And once again, I want to design this local decoder, which given a particular location I, probes a certain number of bits from the first sequence, a certain number of bits from the second sequence, and outputs an estimate of xi and yi. Okay. Once again, the goal is to understand what are the fundamental limits of this local decoding error probability versus the number of bits that I need to probe, which I call the local decodability. Okay. Any questions? Okay. So as before, I'll assume that our schemes are non-adaptive. So for a given I, the set of locations to probe is defined beforehand, before these sequences are actually compressed. But all of this design is assuming that we all know what pxy is. And the local decodability is basically the maximum number of compressed bits that you need to probe to recover any pair of symbols xi, yi. And the probability of local decoding error is also standard. Okay, it's a simple problem. So now we can talk about the baseline scheme once again. You basically do the same thing. You split the source sequences xn and yn into chunks of b symbols each, and then use a standard Slepian-Wolf encoder on each chunk. If you want to recover a particular chunk, then you just use the Slepian-Wolf decoder on the corresponding chunk. So maybe let's say you want to recover this symbol and this symbol. All you have to do is read this chunk and this chunk and use the Slepian-Wolf decoder and recover what you want. Okay. So clearly, since the probability of error of the Slepian-Wolf scheme decays exponentially in the size of the block, and the block size is b, the probability of local decoding error decays exponentially in b, but the local decodability is some constant times b. So the probability of error also decays exponentially in the local decodability. Okay, so once again we have this exponential relationship between the probability of error of this local decoder and the local decodability, the maximum number of bits that you need to read to recover a particular symbol. Okay. So the natural question is it possible to achieve strong locality as we had for the point-to-point case? Is it possible to construct separate encoders and a single local decoder which operates at any rate R1, R2 in the interior of the Slepian-Wolf region? It achieves a constant local decodability, and the probability of error is vanishing in it. We don't really care how fast it decays, but as long as the local decoding error probabilities decays with n, and the local decodability is a constant independent of n, we are happy. So is it at all possible to achieve this? Now, clearly, if you're allowed to compress the sequences at rates above the respective entropies, then it is possible. You use a separate, you just use the point-to-point locally decodable scheme for xn and yn, and you can achieve strong locality. But surprisingly, it turns out that if you want to achieve a non-trivial rate pair, that is either R1 is less than the entropy or R2 is less than the entropy, then it's in fact not possible, at least for a large class of sources. For most sources of interest, it turns out that it is not possible to compress them to operate at specific rate pairs and achieve strong locality. All right. So maybe I'll pause here for a moment, and see if there are any questions. So we originally assumed that it would be possible to achieve strong locality and it should be easy, but it turned out that once we played a few tricks, you can show that it's in fact not possible. All right, and it turns out that this holds for, as I mentioned, it doesn't hold for all sources. It holds for this class of sources, what I call confusable. So we say that a joint distribution Pxy is X confusable if for every distinct pair of symbols, there is at least one for every X and X prime, there is at least one Y which confuses between X and X prime. So given a particular Y, it's possible that X could have occurred or X prime could have occurred. All right. So Pxy of x comma y is greater than 0 and Pxy of x prime comma y is greater than 0. So in particular, if the joint distribution has full support, then it is both x confusable and y confusable. But the following is a more interesting example. So if you look at suppose you take an x which is, let's say, Bernoulli half, and you pass x through a BECP to get a y, then this particular joint distribution, this is x confusable, because for 0 and 1, the erasure symbol confuses these two. So the probability that x equal to 0 and y equal to erasure is greater than 0, and the probability that x equal to 1 and y equal to erasure is also greater than 0. So this is x confusable, but this is not y confusable, because in y, 0 and 1 can never be confused. Right? There is no x symbol which can confuse y equal to 0 and y equal to 1. Okay, so as long as our results essentially hold for this class of x confusable sources. And our main result is the following. So it's possible if you want to do Slepian-Wolf compression of any xn, yn, where the joint distribution is x confusable, and you try to compress xn to any rate below its entropy, then essentially it is impossible to achieve strong locality. You can only achieve weak locality. But on the other hand, if it is not x confusable, then it is possible to compress xn to some rate below its entropy, and R2 equal to h of y, for which strong locality can be achieved. So loosely speaking, x confusability is kind of necessary and sufficient for the necessity of weak locality, but it's not possible. But this does not mean that you can compress it at any rate below R1, below entropy. There exists some specific rate which is less than entropy, and R2 equal to h of y. Okay. So maybe I'll take 5 minutes or so to at least give an overview of how one tries to prove this, if that's okay.
Yes, please.
Yeah, go ahead, Shashank.
Yeah, thanks. All right. So in fact, we have an even stronger result. So if you try to compress xn to any, give yn for free. Okay. So the local decoder is allowed to probe at most d local bits of the compressed version of xn and has complete access to yn. Even then, the probability of error is lower bounded by 2 to the minus some constant times local decodability. So if the local decoder is allowed to probe a constant number of bits of the compressed version of xn and has complete access to yn, then even then the probability of local decoding error is bounded from below by a constant independent of n. Okay, and to see why this is the case, let's take a simple example of the following source. So it's what is sometimes called the doubly symmetric binary source, wherein you have where each component x is Bernoulli half, and you pass x through a BSCP to get y. All right, so that's how the joint distribution is specified. So this implies that both x, the marginals of both x and y are Bernoulli half, but they're correlated. In particular, yeah. So these two are correlated. Okay. So this is of course an example of an x confusable source. It's also y confusable. So let us consider any scheme which compresses xn to some rate CNR, where r is strictly less than 1. So xn is compressed to any rate r less than 1, and the decoder has to estimate xi given just a finite or a small number of bits of the compressed version and free access to yn. Okay, so that's the simpler case. Okay, and the key tool used to prove this is what is called reverse hypercontractivity. So it's a nice property that distributions with full support satisfy. So if you have any distribution pxy which has full support, and xn and yn are distributed according to pxy, then for any sets s and t, the probability that xn is in S and yn is in T is lower bounded by the probability that xn is in S raised to some constant times the probability that yn is in T raised to some constant. So if xn and yn were independent, then of course this would be probability that xn is in S times the probability that yn is in T. But on the other hand, if they are correlated, but the joint distribution has full support, then this can be lower bounded by the following quantity, where these constant beta and gamma don't depend on n, but they only depend on xy. So beta, gamma are functions only of pxy, but not of n. All right. So we basically only need this particular, so reverse hypercontract. So let's look at the following. So I have xn and I'm compressing it to CNR at some rate below 1. Now xn is IID Bernoulli half, right? So just by the source coding theorem, the lossy source coding theorem, you can show that there's at least one component I for which, given only the code word or only a finite or only a constant number of bits of the code word, the probability of decoding error is at least delta, right? So essentially, think about it in the following way. So we want to analyze any local decoder which has access to some particular locations of CNR and YN. So the local decoder has access to this and to this. Now let us first see what is the probability of error given only this, and see how that probability of error changes if you also have access to YN. Now if you have only a small number of bits of the code word, which is compressed to rate less than 1, then there exists at least one I for which the probability of the map decoder is bounded below by a constant, some constant which depends on the rate and the distribution. Okay. So now given this, our goal is to, of course, determine whether xi equal to 0 or xi equal to 1. So essentially, to analyze the probability of error, all we need to do is analyze the probability of error of the following hypothesis test. So there are two hypotheses, H0 and H1. H0 is that xi equal to 0, and given that given a particular realization of the compressed bits. And the second hypothesis is that xi equal to 1, and for the same realization of the compressed bits. So it is as though you're picking an xn from this set S0, the set of all sequences for which the compressed bits is equal to C and xi equal to 0, and the set S1 where the compressed version is C and xi equal to 1. Okay, so you know that the realization of those compressed bits, some specific locations of the compressed bits, and you also have access to yn, but yn is obtained by passing xn through the BSC. So the goal is to lower bound the probability of error of the following hypothesis test. So pictorially, you have xn. So conditioned on the realization of these compressed bits, you know that xn lies in some particular set. If xi equal to 0, then it lies in set S0. If xi equal to 1, then xn lies in some set S1. But now xn is passed through a BSC. So these are sort of spread out and you get confused, right? So the source of confusion is that you observe yn and not xn. If you could observe xn, then the hypothesis test is trivial, but now you observe yn. And the goal is to lower bound the probability of error of this particular hypothesis test. Now, instead of lower bounding the probability of error of this hypothesis test, we try to solve an easier problem. So let us look at a modified hypothesis test where now you have xn, which is either in S0 or in S1. But the hypothesis that if xn is in S0, then you observe it exactly as it is. Then yn is equal to xn, right? So it's passed through a BSC 0. But then if xn is in S1, then it's passed through a BSC P. So there is some probability that the yn could lie in the set S0. Okay. So if right, so H0 is the case where xn is in S0 and it's passed through a BSC 0, whereas H1 is the case where xn is in S1 but it's passed through a BSC P. So at least intuitively, one could think that you have an error. So you have xn, which could lie either in set S0 or in set S1. All right. So if yn is in the set S1, or in fact anywhere outside S0, then it is clear that xn should have been in S1, right? Because if xn is in S0, then yn is equal to xn, right? If xn is in S0, then basically yn is equal to xn. Whereas the second hypothesis is that xn is in S1, but yn is observed as the output of the BSC, right? So we could observe a yn anywhere over here only if xn were coming from S1. Lies in S1, but yn lies in S0. So you draw a random xn from S1, but then after passing through the BSC, this lands in S0. Okay, and the probability that this happens turns out to be, you can lower bound this using the reverse hypercontractivity result, and this turns out to be just 2 to the minus some constant times local decodability. So essentially, this is related to the probability that xn is in S0, but the probability of this happening is whatever, it's 2 to the minus some constant times the local decodability, and the probability that this happens is also 2 to the minus some constant times local decodability, and these constants beta and gamma are independent of n, so therefore you get the following lower bound. All right. So similar ideas hold for general distributions with full support. You can use reverse hypercontractivity, but then for more general X-confusable joint distribution, it gets a little more complicated because we cannot use reverse hypercontractivity. So for this, we sort of mitigate this by low bounding this using a different probability with a joint distribution with full support. Okay. So one last comment. So essentially, this means that the baseline scheme is kind of optimal, right? Because baseline scheme achieves weak locality. And for Slepian-Wolf coding, we've shown that strong locality is impossible. But still, there is a problem with the baseline scheme, and that is once you encode it, once you fix a particular B, there is no way of achieving a lower probability of error. So suppose you take B equal to some constant independent of n, then the probability of local decoding error is a constant independent of n. But even if I were to read the entire compressed sequence, I cannot achieve a lower probability of error because each chunk is encoded independently. So we designed a separate scheme in order to sort of solve this particular problem. So you can compress at any rate point within the interior of the Slepian-Wolf rate region. But then in addition, if you want to achieve a lower decoding error probability, then in fact it is possible to do so by probing a larger number of compressed bits. So it's slightly worse than what in principle can be achieved. But for any given target probability of local decoding error, the local decoder probes a polynomial in log 1 over epsilon number of compressed bits, and in order to output an xi hat, yi hat, and the probability of local decoding error is at most equal. All right. So in particular, if you want a constant local decoding error probability, then in this scheme, it is enough to probe a constant number of compressed bits. But then if you want a local decoding error probability which decays with n, maybe as log n, then the local decoder can probe an additional number of compressed bits and achieve a vanishingly small probability of error. All right. So this is essentially all I wanted to cover. Sorry for going a bit over time. Thanks for your attention. All of these details are available in our paper, which has been uploaded on archive. This is also accepted at ISIT this year. So we also have a conference version of this. Yeah. So if there are any questions, I'd be happy to take them now.
Shashank, one question.
Yes.
See, at least in conventional source coding and Slepian-Wolf, linear codes also achieve the compression rates. So
yes.
Here, is there anything which is known about linear codes?
Essentially, you can do it using linear codes as well, right? So the baseline scheme, it doesn't depend on what you can use any Slepian-Wolf coding scheme.
Okay.
So in principle, you could use a linear code for each of those blocks, and whatever is guaranteed by that, you can also achieve.
Oh, I see. So because the reason for linear codes is because the next problem after Slepian-Wolf, which I had, let's say, worked on, was the Corner-Martin problem, which maybe you can kind of think as distributed function computation via random access, let's say.
Exactly.
Does it make sense in your setting? I mean,
yes, it definitely does make sense. And so, yeah, so weak locality can be achieved in any of these settings, right? Whatever multi-user compression problem you have, you just operate on tiny blocks, and you're guaranteed to sort of get a local decoding error probability that scales exponentially in the local decodability. So that's straightforward. But the question is, can strong locality be achieved in certain scenarios or not? So for more general problems, I don't know what the answer is. But at least for most multi-user compression problems, I would say that if you want to operate at a non-trivial rate pair, then strong locality cannot be achieved.
thank you.
No, thanks.
Hi, Shashank, can you hear me?
Yes.
Hi. Yeah, nice talk. Thanks for the talk. It was very interesting. So a question that I will ask is, so your schemes are all like almost lossless. What about your actual lossless schemes where there is zero error?
Zero error. Well, zero error I guess doesn't make sense in the distributed source coding problem.
No, not distributed. No. Yeah, I guess I did mean the original problem. Yeah.
The original problem, you can yes. So this, if you just want random access, then essentially you can achieve the same things. You can achieve strong locality. Where is that? Yeah. So for lossless compression algorithms, it's possible. Well, the probability you can achieve a probability of error of 0, and the local decodability can be made a constant independent of it.
What is the scheme then?
The scheme is you do the following. So the encoder would know if when there is a problem when. Okay, so let me just back down a bit. So in this particular scheme, an error occurs. So you know exactly when an error. The encoder will know if an error occurs for local decoding of an individual symbol or not, right? So and basically, so let me back up perhaps. Yeah. So this is the scheme which achieves strong locality. What you do is the following. If the encoder knows that an error is going to occur for locally decoding any symbol, then it doesn't compress it at all. It just stores the raw sequence as it is. If it knows that it is possible to achieve, it is possible to decode all the symbols correctly, then it compresses the sequence. So the expected length is going to be n times the probability that there is an error plus n times entropy times 1 minus the probability that everything will be decoded correctly. So even this simple scheme will achieve an expected length of entropy, but 0 error. Did that answer your question?
Yeah, that's okay. Yeah, I guess, this would do it. Yeah, I agree. Okay. But I guess these are but this kind of defeats the purpose. Expected, we probably want it to be. What about the worst case? You cannot do better than that? If you use if you actually try to use prefix codes and things, what is the worst case locality? Expected, I'm not sure if it's the right measure. So
no. So this is the expected compressed length. The worst case locality is still a constant.
Okay, no, yeah, okay. All right, well, okay, I'll have to think about what you said. Okay, thanks.
Yeah. The worst case, of course, it's not a practical scheme. So in practice, I mean, things get a bit messy. But at least in theory, it's possible to achieve an expected length. So expected compressed length is n times entropy plus epsilon, and the worst in the worst case, the local decodability is order 1 over epsilon square log 1 over epsilon. So this can be achieved.
Okay, I see. Okay.
Any other questions?
Hi, Shashank. So thank you for the very nice talk. Can we go to slide number 33?
33. This one?
Yeah. So you have this achievability scheme, right?
Correct.
With the error probability at the most eta.
Correct.
So how small can you make eta? So I see that if you make eta to be like exponential in n,
yes. So
it doesn't work. So you have a lower bound, right?
There is a lower bound. It's not quite exponential in n. This constant is important, but I've sort of hidden that. Okay. So you can't achieve exponentially decaying probability of error, but something slightly worse than that.
Okay. So, but do you have any idea of what will happen if I want to make eta exponentially small in n?
You want okay, but then the number of so ultimately what matters is the number of bits that the local decoder is allowed to probe, right?
Correct.
So at least in this particular scheme, if you demand, it is impossible to achieve a probability. Even if you read the entire sequence, it is impossible to achieve a smaller probability of error. You cannot achieve exponentially decaying probability of error.
Correct. But so the statement you made is true for this particular scheme.
Correct.
But can you make it so do you know of any result which is like a strong statement which says that you cannot do it for any scheme? Have you thought about such things?
Not really.
Okay.
But then I guess that's not a regime that you're particularly interested in, because we already have a lower bound, right? So the probability of error has to be, no matter what scheme you use, the probability of error is 2 to the minus order DWC or D-log. All right. So if you want an exponentially decaying probability of error, then you will have to probe a linear number of compressed bits.
Okay. I get it.
Which is, well, you might read the whole sequence directly.
Okay, I understand. Okay, and also,
go ahead.
Sorry. So another question is, so far we have been talking about, pushing constants under the rug. So are you guys also working on making these things more precise? Do you think there is some scope for that?
Well, we haven't thought about it so much, but this is kind of a negative, at least for the multi-user compression problem, it's kind of a negative result. I mean, you can potentially try to get the exact constants over here, but that probably not so interesting.
Okay.
On the other hand, for the single source problem, it's not known. So let me go back. Yeah. So here, the sort of best achievability gets you to order 1 over delta log 1 over delta. So forget about the constant. Even the dependence, the exact dependence on delta is still not known. We know that it is at most order 1 over delta log 1 over delta, and we also know that it is at least order log 1 over delta for most sources. But this gap between these two is still not known. It's not known what the exact dependence should be.
Okay. Okay, Shashank. Thanks so much.
Thank you. Any other?
Yeah. Thank you, Professor Shashank, for the engaging talk. If there are no more questions, maybe we can close.
Sure. Yes. Thank you.
As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks, and you can visit our website for more details. The link to the recorded video will be posted on the webpage. Thank you, everyone, and have a great evening.